Thank you for the introduction. My name is Pétur Hermannsson, and as he said, I'm from the Technical University of Denmark, the Department of Micro and Nanotechnology, and I'm here to give the talk Photonic Crystal Resonant Reflection, Accurate Wavelength Prediction, and Refractive Index Measurements. I'll start the talk by talking about what photonic crystal resonant reflectors are, what they're used for, and then I'll go on to introduce a very simple model for accurately modeling the resonance wavelengths. Then I'll go on to verifying the model, or showing some verifications for the model, and then I'll talk about some applications of said model. Now, photonic crystal resonant reflectors. They are basically optical structures which combine a dielectric grating or some kind of grating in close proximity to a waveguiding area. There are many different configurations of this, but the one we've been mainly interested in is a structure that looks something like this. You have a grating, a dielectric grating of a period lambda. This is covered by a high refractive index medium on top of that, which in turn is then filled. You have a substrate material that then fills those grooves. So the refractive index of this middle layer here is bigger than the both two, like you would have in a waveguide. So what happens is when you actually illuminate this structure with broadband light at normal incidence is that you actually diffract light into the waveguiding region. But because of the presence of the grating, you can't really have a bound mode. So this light in this waveguiding region will be decoupled again and will undergo destructive interference in the forward direction with the transmitted light and constructive interference in the backward direction. And this will give rise to a so-called phenomenon called resonant reflection, where you have basically near perfect reflection at a very narrow wavelength interval. Now, depending on whether the light is polarized perpendicular to the grating lines or parallel to the grating lines, you will basically generate either leaky TM modes or TE modes within the structure, which are then reflected. If you orientate the incident polarization at an angle with respect to the grating lines, you will excite both TE and TM modes. The reason why I'm telling you this is that these TM and TE modes basically occur at different wavelengths in the reflected spectrum. And this will give rise to, or this allows the structure to be used basically as wavelength selective polarizers, which I'll touch upon briefly. I just want to make a quick mention that often in the, even though this should theoretically be a single unbroken peak, you'll often get, because of non-collimated instant light, imperfections in the structure, and so forth. You will get like a splitting of the resonance peak, which is characterized by a small dip or notch. And the reason why these structures have attracted the attention of the scientific community is that the resonant wavelength is very highly sensitive to the refractive index of the substrate. And if you actually increase, so the changes that occur in the substrate area, you will actually shift the resonance peak to a higher resonant wavelength. And this has been taken a step further by Brian Cunningham and others, where the surface of these structures, of these photonic crystal resonant reflectors, is functionalized. And when you have a binding of a biomolecule to this functionalized surface, this will again be registered as a shift in the resonance wavelength. However, what we actually were interested in was to see if we could actually take this measured resonance location and actually use that to actually calculate the absolute and correct value for the refractive index, not just say that the refractive index has changed by some value, and doing this without any sort of a priori calibration of the structure. So simply taking the material properties and the geometry into account. So next I'll talk about the model. And so basically the structure we're interested in looks like this. You have this polymer grating, like I said before, has a period of lambda, as is covered by a high refractive index layer on top, and then that's covered by a superstrate. And what we do is we basically model this structure here as a slab waveguide of corresponding refractive indices like this, with the same thickness of the core region as is the thickness on top of this grating here. Now the periods of the structure gets incorporated into the model as a phase matching condition, or you can call this the second order Bragg condition. There's a missing equal symbol there. And the width of the grating grooves and the grating height is basically ignored, as it really just influences the width of the peak and not the location. So we know from optical waveguides that for example, a TE waveguide mode to exist in a waveguide, it must fulfill a certain mode condition, which is some kind of a transcendental equation involving the thickness and then these p's, which is given by this equation here. So what we do is basically we add all these things together, and we solve for the wave vector, which then gives us the resonance wavelength. However, because if you don't have, for example, an analytical expression for the refractive indices, you can't really put the correct refractive indices into the model, because if you want to account for dispersion, material dispersion, you don't know in advance whether the resonance peak will, say, occur at this here wavelength, which would then mean that the resonance wavelength would feel this high refractive index, or the resonance wavelength would occur, say, here, which would then lead the resonance to feel like a lower refractive index. So because you don't know the resonance wavelength in advance, you can't really say what the refractive index is at that wavelength, and you can't really input it into the model. So what we actually did is we got around this problem by actually using an iterative approach. So we're starting with the geometry of the structure, the thickness, and the periods. We just selected some kind of guess wavelength, which is completely arbitrary. And then using measured material dispersion data, we calculated the refractive indices of all the 3 layers at this guess wavelength. We then took those refractive indices along with the geometry, used the model to calculate a new resonance wavelength, and then did this again and again and again until this resonance wavelength converged on to a value within a given tolerance, which was chosen, I think, to be 10 to the minus 10th nanometers, so very small. So this is the model. I just want to now go on to talking about verification for the model. So we fabricated some samples and measured the resonance wavelength that we observed on those samples. And we fabricated these samples by so-called UV nanoreplication, which has been mentioned before at this conference. So we started with a nanostructured silicon master, which had an anti-stiction coating. It had periods in the range of 260 to 470 nanometers, which more or less covered resonance wavelengths in the optical regime, and it had a height of 100 nanometers. And then we dispensed a small drop of UV curable polymer onto that grating, and then put a glass on top of that. So the weight of the glass wafer, and then the capillary forces caused this polymer to actually be equally distributed between those 2 layers. Then we UV cured the polymer through the glass wafer, flipped the structure around, removed the silicon master, and then deposited a thin layer of titanium dioxides onto the surface. And generally, the thickness of the titanium dioxide is somewhere between 25 and 30 nanometers. Yes, 25 and 30 nanometers. And as you can see here, we have on the left we have a SEM micrograph of the silicon master, and then an SEM micrograph of the replicated sample. And as you can see, the replication is quite very defect-free. So as I said before, these structures, these photonic crystal resonant reflectors, act as more or less wavelength selective polarizers. So if you put them in between 2 polarizers that are crossed or have an angle between them of 90 degrees, and you insert this structure at an angle of 45 degrees with respect to the other 2, you will only get transmission at the resonant wavelength. So to explain this a little more, so if you're off resonance, basically you have unpolarized light. When you go through the first polarizer, you have polarized light that's polarized like this with respect to the grating lines. Off resonance, nothing happens. There's no reflection. There's nothing in the system that's interesting, and you just have the same polarization as before. And that light will then get blocked by the second polarizer. However, if you are, say, at TE resonance, so remember that all light that's parallel, all light that's polarized parallel to the grating will be reflected. So you're at the same situation as before, of course, here, and then you lose this here parallel component of the light, which means that there can be partial transmission through the second polarizer, and the only light that you basically have that's transmitted through everything is light at the resonances. So if you are at the other end and you look with a camera, you'll see different colors depending on the surface, the refractive index of the surface. Or if you attach a spectrometer, you'll see these very nice and well-defined resonance peaks. So for various periods, we just show several examples here, and various substrates, refractive indices or substrate materials. we compared the model results to the actual measurements. So this shows the case of an air substrate, and the solid, this shows the resonance wavelength as a function of the grating periods. And as you can see here, these symbols here, they denote measured values. The solid line denotes the model where dispersion is taken into account, and the dotted line denotes the model where dispersion is ignored. And as you can see, when dispersion is included, we have a very excellent agreement between the model and the measured results, whereas if there's when in the case where dispersion is ignored, you have less good agreements. And then we tested this for several different superstrates, and it was always the same case. The model held very well in the case where dispersion was included, but not so well when dispersion was ignored. So these extra curves, they show just for ever higher refractive indices, the last two being two index matching oils. So this highlights the importance of actually including the material dispersion in the modeling. However, this scale is very large, and it's hard to maybe say exactly how accurate the model is here, so I'm showing as well the wavelength shift, which happens when you go from air to one of the other liquids. And as you can see here, we're actually predicting the resonance wavelength within actually half a nanometer's wavelength. And for all of the cases. So then I just wanted to, so we basically now have a model that's is able to predict in advance exactly where the resonance wavelengths will occur. And then what we want to do now is say, like, okay, now that we have an accurate model describing the system, can we actually go in reverse? Can we actually take the measured resonance position of wavelength and calculate what the refractive index is on the top? So basically taking these peaks, these measured peaks, find the resonance wavelength, and then use the model in reverse, and then calculate the refractive index at the superstrates. So I'm showing here some preliminary results where we actually can actually measure the refractive index of the superstrate material accurately enough to get potentially the dispersion of a liquid. So we just by using a combination of different periods, we can actually cause these resonances to occur at an interval between like blue and red. And these are preliminary results, but with some more work and fine-tuning, I expect this to be able to be a very good correlation. Also, of course, if you have a very, oops, well, I seem to be missing a slide, so I'll just end with the conclusions. So we have a simple dielectric device which can be very accurately described by a simple model, and since the model turns out to be so accurate, we envision that this model can be used in various refractive index sensing applications, such as determining a dispersion profile of a liquid. Thank you very much.